Okay, this is lecture 30 on invariant maximality by Harvey Friedman. Please.
Yes, I spent this last week thinking very hard about reorganizing the material yet again, this time in favor of having the most dramatic statement that leads the subject at the cost of not knowing whether that statement's independent of ZFC. At the moment it's open. My gut feeling is that it is independent of ZFC. But I was not successful in doing that. And then uh, there will be this best of all statements, not knowing it's independent. And then there will be some a very natural localization move. I'll call it localization move that strengthens it. So I do know it's independent. And I know it's independent and I can use the same reversal chapter. So I like this better. Everything takes a lot of time, but that's the way it is. Uh, and I'm trying to be careful about it. So now we have 8 chapters. So let's go over what we want. Well, there's introduction, which can't be written yet. There's the new chapter 2 that we talked about last time, which kind of largely replaces the old chapter 3 on derivations, but not entirely, because that chapter was based on local invariance. Um, and we're going to talk about this, of course. Uh, I believe there should be a third chapter here on invariant maximality, but sort of logically based, because this will give, if I set this up right, it will be proof in the same large cardinals. And what will happen is it implies things I've already reversed. So it's equivalent to con SRP over WKL naught. Uh, and if it's set up right, it will have an enormous number of applications of consequences, some of which seem even more and more familiar to standard mathematical situations, uh, increasingly familiar. Although everything I'm doing here is just order. So in mathematics, it really is important that you do something beyond order, but that's a whole nother thing, and it can't be dealt with in this context and with this book. Subsequent treatments on invariant maximality, where you have more structure just than order, is very much important, but it can't be dealt with right now. All right, so then there's the local invariance we talked about. Okay, and this is standard. And then, of course, we have uh, which we started, but I got into this other matter of how to set this book up. And then this hasn't been fully fleshed out either. All right, so let's talk about what I'm doing here. So I have a lot in the by the way, there are 8 chapters now. It used to be 5 or something. But the point is that this doesn't indicate that it's that much more material, some more material, and some material taken out. So it's not that crazy. All right. Now, this chapter 2, which I think I didn't change the title much, maybe a little bit. N shift, N equivalent, and variant maximality. There are two competing kinds of invariants that are used here. Well, there's first of all, there's the order invariance that's completely standard in the for rational tuples. That overrides all notions. We have to talk about order invariant relations from the get-go. Okay. So that's a certain kind of invariance. But there's also n-shift invariance and n-equivalent invariance. And those are the only two uh, ones that are in the chapter 2. Uh, the n-shift invariance is an example of function invariance, and n-equivalent invariance is an example of equivalence class invariance. Equivalence invariance, I might want to call it, because n equivalent is an equivalence relation. And then there's a third kind of invariance called local invariance, and that was what the book was originally just about. Uh, and that's where I was always on one fixed interval minus 1, and there was I was looking at general functions as my one-dimensional functions as my uh, way of talking about the different local invariances. But this chapter is quite different. There's only one function. Well, it's variable on dimension, but there's only one function or one kind of function, one function up to dimension change, and only one equivalence relation up to dimension change. Uh, so the way this is structured is first of all, we talk about the stuff where you don't have invariance. First of all, this is just introductory material of a general sort, which is used throughout the book surrounding simply order equivalence on tuples of rationals. This is um, this is stuff where you don't have the invariance, so there's no logical issues really. It's just some standard stuff about maximality. So it's not invariant maximality. It's just maximality. That's good to separate out. And there's some interesting things in there. Nothing new. Then I actually have some of these whole sections, by the way, are quite short. Like a couple of pages. But I want to lay it out because I want the table of contents to speak volumes about what's going on here. All right, so um, there's the seminal statement of the subject called end-shift inclusion, and that's supposed to entice everybody. However, I don't yet know that this statement is independent, and the only proof I have uses the same large cardinals. Uh, then I can make this statement a little stronger by using invariance because the actual bare statement here doesn't even use it. It's less advanced than invariance. It's just inclusion. You'll see what I mean. Uh, and I will be showing in this big section here, equivalence and implications, I will be showing that these 2.4 and 2.5, are actually provably equivalent. 2.5 being trivially stronger. They're trivially equivalent. Then I actually use any equivalent invariance. Here, there's no notion of inclusion that's really that any good, really. Uh, you just go directly to invariance. And that's another form of the seminal statement. Um, and that also, I don't know how to, that's also equivalent, and I also don't know how to reverse it. But in here, I also have the magic extra ingredient of localization. And I probably will start using the word localization more. Uh, it's a little ambiguous what localization should mean here, by the way. Um, and when I give a localization form, I shouldn't call it. I got to be careful. Uh, I called it local invariance, the other one. Yeah. Localization, I put the isation that should help because I'm using the word local two different ways that have nothing to do with each other. Um, so localized. Yes, I think I'm going to be calling them localized. Although I have some more technical names also. And that's it. That is independent. That is strong. Okay. There's an alternative called emulators, which is an alternative to maximal chains. Maximal chains is what all of this is based on. Emulators is a real competitor to maximal chain. Maximal emulators is a real competitor to maximal chains. We've talked about this before, but not that much. And then I have this chapter that says that everything's equivalent to everything else in the following sense. There's the group of statements, there's the group of statements coming out of the seminal statement. There's a group of statements that's with no localization, and all of those are equivalent, but I don't know what the status of them are. And then there's a completely corresponding group of equal number of statements that have this magic localization in them. And there I also show equivalence. And they're stronger. You just the implication goes that way. And those I know are independent. Uh, so uh, that's the real issue. And then I have these sections, which should be familiar, the reworking of stuff we did many times, of how I prove the statements. Now, the number n, little n, doesn't appear. There's only one numerical parameter in all this, namely k. Now you can, I thought that the second parameter, which you can tease out of this, is not so important or striking here because I'm not using intervals. But the other number is striking in the section in the later part of the book on local invariance. And so a lot of that stuff will be kept uh, in the old chapter 3. Okay. So I first do this in one dimension. See, that's q is q to the 1. I first prove it in one dimension. This is the strong one with the localization form. And the localization form is indicated by the symbol less than or equals for reasons that you will see. That's how I can tell that it's really the ones that I know are strong, the localization form. You'll see why I use less than or equals. So I prove it in one dimension flat out in RCA naught. That's a simple thing. Then I go to 2 dimensions and I prove it using omega 1. And I divide it into 5 bite-size steps. This is the space I use. This is a transfinite space I use. Um, I already see something wrong here. This should be. All right, why don't I get to that? Uh, Invariant maximal choice of R. So I take the problem, I throw it into the transfinite, and then I build an inductive chain by transfinite induction. Chain means, any 2 elements are related. Inductive chain for R. And this is all in transfinite. And then I build I build the S is the inductive chain. I build this structure with these acting like indiscernibles, so to speak. And then I've done all my combinatorics up here, and then I pull it down to the rationals by an isomorphism, and then I can just immediately prove the statement that I want. And that's a very coherent kind of thing. And now we do it in omega 1 gently so that mathematicians are comfortable but uneasy that what transfinite orders even for something like this, right? By the way, I don't have reversal issues or another subject. Okay, so here I just do it. Now I do the full thing on a cardinal kappa. So it's omega 1 here. Uh, here. Yeah. Okay. Except the combinatorics, as opposed to here, the combinatorics is more sophisticated and not accessible in ZFC. You're going to use SRP. And then I fix K. I fix K as long as it's at least three. Um, because dimension two was already handled. Uh, with the same pattern, except that I should put kappa. Yeah. Okay. Then there's an optimality. I just started thinking about this and I haven't cleaned this up. I used to think about this kind of thing. So it's not totally new. I think I know what to do. The n equivalence relation is the strongest reasonable equivalence relation you can use for invariant maximality. That's supposed to be the theorem. And what does a good equivalence relation mean uh, on Q to the K? Well, n equivalence is itself a subset of Q to the 2K. And it's first ordered, and it's quantifier free definable. It's quantifier free definable in the structure Q comma less than uh, comma capital N, where N is a predicate. So I want to look at all the equivalence relations that are definable without parameters, that are definable without, well, I have to be careful. Look at all the equivalence relations that are definable without parameters in quantifier free definable in this structure. And I have to also, I think I have to consider the ones with constants for each and element of capital N. And then there's also the first order definable ones. All this has to be fleshed out. I didn't have time to actually work this out. And I want to determine what I'm looking for is a maximum equivalence relation that's suitably definable. And I want to show that n equivalence is the maximum one that you can use for invariant maximality for the even for the seminal statement. Um, Something like that. I have to work that through carefully, uh, how that's done. Um, and in some cases, in some formulations of this, you get two, exactly two maximal ones. Each one is the reverse of the other. Sometimes you get that when I was doing this. Because Q is symmetric. Yeah. Less than related. Yeah. Okay, so this chapter is old stuff from previous work. You know that these things are um, implicitly pi 1. All the statements, at least with localization. You know, there's an issue about whether the originals. Yeah, it's another little wrinkle in this. It may not be so clear that the seminal statement is implicitly pi 1, but it follows from another implicitly pi 1 statement, namely the localization form. You know, the form that I know how to do, the form I know how to reverse. I wonder what I should make of this. Yeah, I have to think that through. Um, and then finally, we want to link this to the rest of the book so that I know that everything I'm talking about that's been localized, not the original seminal statement, because I don't know how to do that, actually is independent and reverses to con SRP. All right. So let's go through some details. Now, at some point, I didn't get time to format, so it'll look kind of crazy. Okay, so this 2.2 is nothing new, is old material expository background material about order equivalence on tuples of rationals. And the first order theory of Q comma less than, is in there and stuff like that. Um, Now, the maximality without invariance, I think we talked about it last time. Just go briefly through that. Uh, First of all, the whole subject is based on, well, largely based on chains and relations, and that can be done very generally. A relation is a set of ordered pairs. A maximal chain in a relation is a chain in R, which is not a proper subset of any chain. A relation on X is an R contained in X squared. Now, some definitions of chain are that any two distinct elements are related, not just that any two elements are related. And the way I was going to handle that is, well, this is simpler, obviously, and also interesting, because if you're reflexive, the two notions are the same. So I was going to use the notation chain not equals, that kind of thing. And that works well. That kind of thing works well. But that's involved in invariance. And I think that I'm going to have this extra chapter that I described uh, based on AE properties, which is going to handle all at once all possible variants that I had in mind. So, for example, if I take all this work and replace chain by chain slash not equals, everything goes through. Everything is the same. You can prove equivalence between the versions with chain and chain unequal. But that should be but there's so many variants possible. You can go to graphs, you can go to this, you can go to, that I'm looking for a much more a general theorem, which I think I more or less have, but I want to make it as general as possible. So, uh, I'm taking chain to me be any two things are related. You can object to that, but it doesn't make any difference. All right. And then we talk about what happens in the general case, which is the axiom of choice. Every relation has a maximal chain equivalent to the axiom of choice. Uh, Now, if the relation is countable, then you just need RCA naught, and if the relation is finite, you can formalize everything in EFA and prove it in EFA. Yeah, so that's all very familiar stuff. But then we go to an order invariant relation, and an order invariant subset is defined there. Every order invariant relation. So maximal chain slash QK means every order invariant relation on every Q to the K has a maximal chain. So this is a special case of what I said before. The point here is that you can actually formalize this and prove this in EFA because you can describe the maximal chains and actually you can do this with exp. You can make them exponential time and even use that as a formalization, a more specific formalization even. And so I proved all that, yeah. But it'd be interesting to go more deeply into the computational complexity of the situation, with completeness and so forth. Uh, okay. Now we get to the seminal statement. So this is what I really think the mathematician should look at first. So there's a thing called the end shift, and it maps each QK into QK, where the end shift of X is obtained by adding 1 to all Xi for which every Xj greater than or equal to Xi lies in N. Okay, that takes a little bit of thinking to digest, but it's obviously some sort of capital N tail, right? And then I'll give a better set of examples that makes it very friendly. starting at two coordinates or something. But anyways, here's an example of where the end shift is in action, and the end shift over here doesn't do anything because the top the top coordinate is 7/2. And the end shift of a set is just set of all end shifts of its elements. So here's the statement that I want to push to get everybody interested. Every ordered relation on every q to the k has a maximal chain containing its upper shift. Every ordered relation on every q to the k has a maximal chain containing its upper shift. It's not even, I don't even use invariance. All right, I would like to reverse this. The second desire is I prove it, that it's weak. I mean, that it's not strong, so to speak. Yeah, I haven't been able to quite see my way through this. If I had to guess, I would guess that a modification of my chapter 4 might actually do it. Which is, I don't like changing chapter 4 at all, but I'm going to take a hard look at this because it would certainly simplify the discussion if I could just. Now I put the inclusion sign inside here. You can see the end shift is in the name. Oh, I'm not upper shift. I'm sorry, end shift. That's a whole nother story. I'm going back to old stuff that. All right. Sorry, end shift. Every ordered invariant relation on every q to the k has a maximal chain containing its end shift. Yeah. You add one to the end tail, so to speak. All right. We prove this statement using large cardinals, uh, but I don't know. We prove a natural localized form of this, a natural localization of, localized form or localization of, oh, I want to move to staying away from this word local without some change, or localization of in section 2.9. We prove it. And for this refinement, and for this, let's get rid of it here. And for this localization, we show in section 215, relying on chapter 4, that use of the large cardinals is required. For this localization, we need to strengthen the notion. For this localization, we need to strengthen the notion of maximal chain. Okay, so for any subset of q to the k, a slash less than or equal to n is just a intersect the tuples below at or below n, okay? And now we have the statement, every order invariant relation on every, okay, first of all, this is the one that doesn't have the, oh, and it does have the inclusion, I'm sorry. Yeah. Okay, every order invariant relation R on every q to the k has an S containing its end shift, where each S slash less than or equal to n is a maximal chain in R slash less than or equal to n. Now, I should remind you that n is k and n are, by convention, early in the book, variables ranging only over the positive integers. Actually, this will work. This would in fact work. I'm not sure about that. I was going to say it should work for any integer n, but let's not go there. Okay, so k and n are actually just variables over positive integers. Yeah. Okay, now we can more vividly compare these two statements. This is just a less than or equal there. See, I just have less than or equal there flat out because of the fact that these truncations are coming in. See, we can more vividly compare this and this by rewriting this, the original one as follows. Uh, so we can write the original one. Every ordered invariant relation R on every Q to the K has an S containing the end shift, where S is a maximal chain in R. That's just making the statement more awkward in English. And then we can compare it with this statement up here. See, every ordered invariant relation on every Q to the K has an S contained, where each, you see, instead of S is a maximal chain in R, each S slash less than or equal to N is a maximal chain in R slash less than or equal to N, right? So that's the localization form. All right, and it's easy to show that this implies this. You put the less than or equals there. This doesn't belong there. Yeah, I'm not doing proofs in here. Yeah, this is trivial, anyways. All right. Now the other direction is going to be done in my massive equivalence section. The other direction, actually, and this involves the stuff that I don't know how to. This involves the stuff I don't know how to reverse. I'm sorry, I don't have the other direction. I'm sorry. This direction is trivial, and I don't have the other direction. If I had the other direction, I would know that the seminal statement, which is this, was already independent, which I don't know. Okay. Then we go to invariance. There's many important invariance notions in math, and we only consider three broad types: function invariance, equivalence invariance, and local invariance. We've already been using equivalence invariance with the order invariant notion. And in this section, we use function invariance. In this section, not this chapter, we use more. Here is the most general relevant formulation of function invariance, and I describe what it means to be F invariant with ambient spaces. Note that here the x-axis is the ambient space. However, in this chapter, we're only going to use the end shift on the Q to the K, and that maps the ambient space into itself. Thus, we are in the simplest situation where the function maps the ambient space into itself, of course. The simplest situation. All right, we have two statements now. The first one is before. The first one is this one in the previous section. And then we have this one, this new one where we use invariance instead of inclusion. We go to invariance. Okay. And this is trivial that actually the one without the inclusion, the invariance, the one with invariance implies the one with inclusion. That's trivial. But the other direction will be proved in section 2.8. So these are actually equivalent. The invariance you can get from the inclusion. Then we go to the other notion of invariance and equivalence invariance and equivalent invariance. And that's defined. First of all, we want to define what equivalence invariance means in general, and that requires talking about relations, maybe relations not on a given set, just relations abstractly, and abstractly an equivalence relation, by the way. An equivalence relation can be defined abstractly without having without it being on an X. You can do that. You use the field in an obvious way. And S is E invariant if and only if for all x, e, y with x and y in the ambient space. The ambient space for this. We have equivalence. Now, in this chapter, we use only the n-equivalence relation on the q to the k. Thus, we're in the simplest situation where the equivalence relation is on the ambient space. Now, this n-equivalent is defined below. The n-tail of x is the part of x that consists of the xi for which every xj greater than or equal to xi lies in n. And x, y, and q to the k are n equivalent if and only if they're order equivalent and they agree off their n-tails. The numbers in the n-tail of x are held in place, right? In other words, they just stay on the sequence. Now note that the n shift of x is the result of adding 1 to the n tail of x. And I didn't want to define the n shift using the n tail because it was much quicker and direct to simply define it the way I define it, which is to bypass the definition of n tail. And the n shift of x is obtained by adding 1 to all the xi such that every xj greater than xi lies in n. However, that becomes more awkward when you want to define n equivalence. And so separately defining the n tail is better. All right, this is just fine points of exposition. And now we can spell out the definition. N equivalent invariant if and only for all n equivalent x and y in q to the k. X is an S if and only if y is an S. And now we have three statements, the first two from section 2.5. You have three statements in play. The original localization of the seminal statement, then modifying it to be invariant instead of inclusion, and then simply going to instead n equivalence invariance. Okay. N equivalence implies n shift. N equivalence implies, I'm sorry, x and n shift of x are n equivalent, and n equivalent invariance implies n shift invariance and not the reverse. However, these statements, so you have these statements trivially like this, and in section 2.8, we'll prove all three are equivalent over RCA naught. Okay. The other modification that's very important is emulators. Emulators for finite sets, you might as well, are an important alternative to chains in order invariant relations. So S is an emulator. This is an old definition we've used. Go over it again. An emulator I'm just formatting this. At some point, I will stop formatting. Too much to do. Okay, an emulator means any pair in the set in the emulator, any pair in the emulator is order equivalent to to some pair in the thing that's emulated. It's a very attractive notion. And here is our seminal statement with emulators. Every finite subset of every q to the k has a maximal emulator containing its n shift. Every finite every order invariant relation on every q to the k has a maximal chain containing its n shift is the seminal statement. And MEM stands for maximal emulator, and in our big equivalence chapter, we'll show these are equivalent. That emulators and chains are closely related. That's not entirely trivial to do that. An emulator is really kind of weaker than maximal emulator is kind of weaker than a maximal chain, but you can still simulate the chain combinatorics in the emulator combinatorics. S is an emulator, so we have to so in order to state the less than or equal stuff, we need this definition. S is an emulator of finite E, maximal in V. This may be confusing if I don't format it a little bit more. If only if S is an emulator, which is not a proper subset of any emulator that is included in V. Okay. Okay, so we have these three different forms. Every finite E has an n shift invariant S where each, yeah, okay, S where each S restricted less than or equal to n is an emulator for E maximal in QK less than or equal to n. And we could do this for n equivalent invariants. And we show that these are equivalent. We're going to show that those are equivalent also over RCA naught. Okay, I'm not going to do this, but I talk a little bit about it. This famous equivalence and implications, how do I organize all this stuff? Actually, the count is, yeah, the count is that there are 12 statements involved here, naturally involved. And they're in two groups of six. They're in two groups of six, and each group, they're all equivalent to each other in RCA naught by elementary argument. But group B is stronger than group A, and I don't know how to go from A to B because I don't know whether the seminal statement is in fact independent. See, this whole thing is equivalent to the seminal statement. Yeah. Okay, so then we have the ones that have, these are the localizations. The localized statements. All right, and these are separately shown to be equivalent. Um, One, two, three. Three kinds of serious implications here. How do I go from end shift containment? That was what I mean. I'll go from there to end shift. How do I go from end shift to end equivalence invariance? Um, yeah, how do I go from end shift inclusion to end shift invariance? And how do I go from end shift invariance to end equivalence invariance? And how do I go from maximal emulators to, this is A means arrows, to maximal chains? We proceed in the following order. This just gives a plan of attack of how I do it. First, do that in group A, and then in group B, somewhere, blah, blah, blah. That's the strategy, how that chapter goes. Okay, then we have uh, the proof in one dimension. In one dimension. Uh, First of all, this is when I was using intervals. Well, you can actually list list all these things. There are only 8 of them. Yeah, and then you can use that to prove the statement because you have so much control over what's happening here. And then the first one that's serious is dimension 2. Um, and we talked about the 6 stages in the introduction. The space that you're going to use is a copy of the rationals up front, then followed by omega 1 cross 0, 1. That's the rational interval. Union, at the end, there's one single special point, omega 1, 0. And there are 2 orderings. The first one is dense, and the second one is a well ordering. All right, so uh, Yeah, this is the definition of these orderings. We've done this many times in different contexts, the same thing. There's nothing new. Uh, then we define invariance like this. Uh, at some point, we do the combinatorics. Yeah, we build this inductive chain. We do this transfine induction. X and W in the space W lies in uh, X and W squared lies in the chain if and only if the set of earlier things is a chain, including X itself is a chain in R. In other words, you can add it on and stay a chain. This is red inductive chain. And you can prove standard techniques that this is well defined. And then you can prove that the inductive chain I just defined is in fact a maximal chain. That's pretty easy. Okay. I'm not going to go through all this. I mean, because it's stuff we've kind of done in different guises. Uh, but it's streamlined and clearer, and also it's done in a way that uh, it's done in a way where when you lift it up to to a big cardinal, you can see exactly how you get blocked and how you need something special. The combinatorics needs to be improved. The combinatorics you use for omega one proof uh, is kind of binary. Well, k equals two. Uh, but if k is arbitrary, you're going to have to do something uh, that's not available in ZFC. And I know that has to be for this. All right. Um, so I haven't worked it through, but I want a section here on optimality of n equivalence. The idea here is that the n equivalence relation on each q to the k is a subset of q to k, uh, is a subset of 2k which is quantifier free definable using less than an n as a predicate. Uh, yeah, right. You have to say why that is, but that's okay. That'll work. And I think there's only two maximal equivalence relations so defined that can be used for the seminal statement, and a maximum one that can be used for the the localizations, let's call them. Okay, now the other point is chapter 3 came about because I thought of a huge number of important invariant maximality statements, most of which can be derived from the ones we've considered, but not all. I think I found the right unifying principle. I haven't worked it out properly. A far-reaching extension of the statements of the localized statements that uses some basic logic to formulate. Yeah, some of these. First of all, there's some obvious variants that are kind of a nuisance to do. They're kind of silly and easy and all that. Uh, like changing cliques to clique slash unequals, i.e., or going to graphs or various things like that. But also there's a whole nother brand of these that I think works. That is, you can ask for, given a relation, a subrelation, given a relation on a set, a subrelation just means a subset of that relation, still a relation, right? Um, and then there's also the notion of restriction of a relation. And then that's restriction to a one-dimensional set, right? These are two different notions. Uh, and the things that I'm thinking of that seem like they're very mathematically oriented is well, maximal chain is pretty much, but also given a relation, you can ask for a maximal subrelation that's univalent, maximal subrelation that's bijective, maximal subrelation uh, uh, which is what do you call that? Complete. Uh, complete means any two things in its field are related, both directions. Yeah. All right. So you can ask for a maximal subrelation or a maximal restriction satisfying some property like that. And these are all amenable. And then you want to get an invariant example. Suitably invariant example, like n shift invariant or x any equivalent relation, an equivalent n equivalent invariant. You can ask for that, and that seems to work. And I don't think it's not in full generality, it's not covered by the statements we're talking about. It's a little bit more. And so that leads to the project of really stating the most general forms of this. And I think that the four logical form A star E star is going to be useful for this. I have to think it through. Um, and um, and if you do that, you'll get statements that are uh, provably equivalent to the large cardinal consistency. And well, you'll get statements that immediately imply a flood of consequences of the kind I was describing. You know, so I think that's very much worthwhile to do that. Um, but I haven't fleshed it through completely. All right, so that's where I'm at right now, and I think things should be cleaning up quite a bit next time. Uh, things will be much better shape. Uh, we might be able to have the third lecture on this chapter as the final lecture on this chapter. I won't promise that because some things come up, but I think there's a good chance of that. All right. Thank you.